Hey there, wanted to let you know this is an audio only podcast, and if you get your podcast on Spotify, you can go follow me there. All right, cheers. Hello there, ladies and gentlemen. Welcome back to the Ephemeris podcast. I'm your host, Aphelion, as always, and if you are new to this show, this is a podcast where we look into new stories coming out of the world of astronomy with 3 stories per episode. So, the 3 stories we have for this week are firstly, a new source of high energy neutrinos that has been confirmed or very close to being confirmed. We have T Corona Borealis and its next explosion, which is bound to happen soon. And lastly, we have a story about a hypervelocity star and where it might have come from. So, without further ado, let's get into this first story here. The history of our understanding of neutrinos in the universe is not very dated. At least I wouldn't say the 1960s was the first time that neutrinos from the sun were detected, and we've been expanding our detection ability of neutrinos in the universe ever so slightly over the last few decades. One place we've seen neutrinos produced in some of the stories that we've talked about is in white dwarfs, which, yeah, once again, talked about that before on the podcast. And there are some other candidates to consider with the production of these tiny quantum particles, such as blazars, supernovae, and then black holes and active galactic nuclei. In 2022, a Seyfert galaxy named NGC 1068 was found to likely be producing high energy neutrinos, and this is where we developed the idea that maybe Seyfert galaxies and what they contain might be the center of neutrino production. And so that's where our article today steps in to add to the story of these relatively new candidates that we've discovered. 2 teams using data from IceCube, the world's premier neutrino observatory located in Antarctica, have independently identified Seyfert galaxies as likely neutrino producers. Now, before I go any further, there is some clarification that needs to be made about what Seyfert galaxies are. So they're galaxies with active nuclei similar to quasars. We call them AGNs, active galactic nuclei, and I'll probably try to refer to them as AGNs for the rest of the story here. And these AGNs that are within Seyfert galaxies, they shine as bright as the entire Milky Way. They are very, very bright. But they are, as a whole, closer and less luminous than quasars. They're not quite the same. They make up about 10% of the galaxies in the universe, and they're strong in radio emissions for obvious reasons, because AGNs produce radio jets, very strong ones, and Seyferts are also strong in ultraviolet radiation due to the accretion disks that they have. Another characteristic of Seyferts are their broad emission lines, which indicate high ionization, which basically just means that the gas in Seyfert galaxies, it's hot, expansive, and energetic enough that some of the material in it, it's missing multiple electrons. So you might say they're like doubly or triply ionized. It's not been specified, but that's the assumption here. So you can get the idea that these galaxies probably have produced some other high energy subatomic particles or quantum particles. To specifically find evidence of neutrino production, the teams of researchers looked at the physical properties of the corona of the black hole in the AGN, and it's similar to looking at the corona of our sun and seeing these amazing sort of ejections and emissions coming out of it, but on a grander scale, I would say. And this region of the black hole is very hot, which is why we're looking at it, and that can be interpreted in both ways, like as in, it has a high temperature, or as in, hot in the sense that there's a lot of heat. There's an important difference between the two in your standard thermodynamics, but the difference here is a little bit negligible because we're not looking at gases in like when they're like isolated, in a container or something, and you can't really do work on this kind of gas as easily, if you get my point. So yeah, that is what we understand about the corona of the black hole in the AGN, and why we're looking at that part of the Seyfert Galaxy to look for neutrinos. So the exact findings that led to Seyfert's being clear candidates isn't specified here, but the conclusion that we got from the research, which is that they're highly likely to be neutrino producers, it leads the way for more research on cosmic neutrinos. Now that we know that Seyfert's AGN are key for neutrino productions, we can start to look into other galaxies or sort of like similar structures that might have like black holes that are likely to produce neutrinos, and then we can find some other candidates beyond just Seyfert's. So yeah, that is the first story we have about high energy neutrinos and where they might be coming from. Our second story here is about a very specific star that we're already pretty familiar with. It's T Corona Borealis, and there's some recent news that brought to light that its next explosion will be happening close to September 2024. So what exactly is this star, and what do we know about it, since there's so much we know about it? It's a recurrent nova, and you guessed it, the Corona Borealis constellation. And I'm surprised I did not talk about this star in the episode about recurrent novae, because we have an episode on that, which is in season 1. Feel free to check that episode out if you want to at a later time after this episode. But now is the perfect time to bring up this specific recurrent novae that we know about, or nova. T Corona Borealis, its first outburst was seen in 1866, but the star was discovered before that as a regular magnitude 10 star. We know that it's a symbiotic binary system with a red giant and a white dwarf with 1.3 suns worth of mass, which is pretty close to the Chandrasekhar limit, so don't think it's going to get any better than that. And during T Corona Borealis' outbursts, the magnitude usually goes from 10 to about 2.5, which puts it at a magnitude where you can actually see it with the naked eye. The last outburst was seen in 1946, so it's due for an explosion. It's a once-in-a-lifetime event since it occurs once every 80 years. If you're very, very attentive to detail, you may have noticed that 2024 isn't 80 years after 1946, if we are to go by that logic. So then why do we know that it's happening in September 2024? That is due to the fact that recent observations have shown a dip similar to the pre-eruption dip we saw in 1946. And an important part about this explosion is its pace. The binary is expected to explode in a matter of hours, and its peak brightness will only last half a day. So if you've got like a backyard telescope or binoculars that are appropriate for this kind of thing, you probably want to follow the Corona Borealis constellation very closely, like every single day, because if you don't, you might miss out on it. So this is a really good opportunity to observe something cool that we don't usually see in the universe. I'd say comets, like Halley's Comet, is around the same frequency as well. So this is something that can be put in that caliber of, I guess, beyond Earth events. So it's definitely something you should look out for if you have the observational capabilities, which most people will. The peak brightness is only going to be for half a day, but the actual like sort of brightness or increase in brightness that occurs because of the explosion as a whole will last about a week. So if you don't see the peak brightness, you will at least be able to see it fading away. So yeah, that is a very short story here about T Corona Borealis, which is nicknamed the Blaze Star. Our last story here is about a hypervelocity star, as I mentioned at the beginning of the episode. But I tell you what, it is seriously seriously fast. This is moving rapidly through the universe. When I say seriously fast, I mean 1.3 million miles per hour, which is 1,500 times faster than the speed of sound. So that's 583 kilometers per second in a second. If you want to put that into perspective, the star would make it around the world in 1 minute and 10 seconds, ignoring gravitational effects, obviously, but that is still extremely fast. And its speed is more than 7,000 times faster than a bullet train and 5,000 times faster than the fastest recorded F1 car speed. So how did we get such a fast star? Because, that's pretty impressive. If it gets around the world in 1 minute and 10 seconds, it gets across the US in about like less than 10 seconds, which is really, really fast, right? That distance is covered in a matter of, a very little time. So anyways, how did we get this so-called hypervelocity star? We suspect it ended up in one of two precarious situations, but before we get there, I do want to talk about the star's characteristics and its analysis first. We discovered that the star was an L sub-dwarf, which is very far down the Harvard spectral classification system, and it isn't even included in the standard OBAF GKM order most of the time because it's a very, very small portion of the stars in our universe. And their radii is measured in Jupiter radii because of how small they are, and their temperatures are very cool for stars in general. You can go a little bit further down the classification system to find Y stars, which are like almost room temperature. But yeah, L is also part of that, group of really, really small and unusual stars. It's also very low mass, so in some situations, these stars are seen as gas giants rather than stars, but not always because there has to be, it has to be orbiting something or, all that jazz. But anyways, L-type stars, very, very special, not commonly seen in the universe. And this is why, to be able to do spectral analysis on the star, researchers had to use its infrared spectrum, because when you have, sort of temperatures of like 2,500 Kelvin, the only good way to observe the stars through its heat radiation, which we can see through infrared. So let's go back to the two leading theories that we suspect has caused this really small star to go very, very fast. The first theory is that the star was ejected from a Type 1a supernova event. We've talked about Type 1a supernova enough on this podcast, so I don't feel like I need to explain their whole dynamic, but if you haven't heard of them, basically they're sun-like stars that feed white dwarfs, which explode under their own mass. And when this happens, the white dwarf also just disintegrates, so it's possible that a sun-like star could get propelled at, a little bit more than its original orbital speed after the event. And that's about as simple as it gets. Then there's the other theory, which is definitely a bit more dank, which is that this star was within a globular cluster and was close to the center of it, where there were two black holes, binary black holes. And the dynamic between these three bodies, which isn't very predictable, but nonetheless, the dynamic between these three bodies caused the star to get flung out of the globular cluster, in fact, at a speed that could make it escape the Milky Way, which is actually quite a scary thought, because you don't hear about that very often. And yeah, it's definitely not something that we have heard of ever, I think. So what we could use to validate this theory, since it's so left field, I guess you could say, is we could use a handful of simulations, which was produced by the researchers. Actually, they utilized that, and it turned out that this scenario is actually possible in some occasions. So it's the reason why we bring it up, and this is actually probably the more prominent theory that the researchers went with. during their study. So that's this sort of simulation stuff is the basis for this being the leading theory. What I would say about the theory, in my opinion, is that it does take something quite spectacular to make the star fling away from two black holes at the same time. My assumption is that somewhere in that simulation, a result was produced where the star got stuck in the crevice between two black holes, and the gravitational fields created like a, I guess, an asymptote, and the star just launched along that um, asymptote in an instant. But I am not very familiar with stellar dynamics, and definitely not enough to know what the simulation did. So that's just a very out of nowhere hypothesis for how that worked. But I'm sure it's very complicated stuff, and there is more research that needs to go into this stuff. So, yeah, that is what I have to tell you about the hypervelocity star, and that will wrap up the last story of this episode. Um, if you all enjoyed listening to this podcast episode, I would sincerely appreciate a follow on Spotify if that's where you're listening, and a subscribe on YouTube if you're listening there. And for my YouTube subscribers, if you have not been getting recommended on my content, I would suggest setting that notification bell to all so that you don't miss out on any of these episodes. I know the returning viewer rate on these episodes is fairly low, so I always try to suggest that so that you all will come back and watch some of these episodes. But yeah, I think that's all I gotta say. I will try to produce some more shorts in the future. I have a little bit of free time to do that, I think, in the next couple of weeks, so I'll try to get on that business. But until the next episode, I will see you all later. Peace.